Bismillahirrahmanirrahim. Assalamu alaikum, respected teachers and my dear fellows. This is me, Aisha Amin, along with my group members giving our presentation. Before starting our today's presentation, I would like to thank our respected teachers, Professor Dr. Nasreen Fatma, Dr. Shazia Nisar, and Dr. Sadaf Iqbal for giving us this opportunity to portray our talent. Now, moving towards our today's presentation, the topic of my presentation is simultaneous determination of the concentration of two species, potassium permanganate and potassium dichromate in a mixture. Some of the contents of these topics are the chemicals and the reagents, the theory, instrumentation, equipments, procedure, observations, calculations, and result. Now, the chemicals and the reagents. The first one is potassium dichromate, the second one is potassium permanganate, and distilled water is used for making up the volume up to the mark. Now, what is simultaneous determination method? A simultaneous determination method is a method in which more than one species can be analyzed at the same time, provided the conditions required for the analysis is obeyed. The conditions for a simultaneous determination method are following. The first one is both the absorbing species should have different area of absorbing spectrum. The second one is there should be no chemical reaction between the two species. They should be inert. And the third one is a difference of about 10 nanometers should occur in the lambda max of both absorbing species. Beer's law can be applicable to a mixture containing more than one kind of absorbing substances, provided that there is no interaction among the various species, even if an overlap in their spectra exists, as the total absorbance of a solution is equal to the sum of all the absorbance of individual components of a mixture. Absorbance is an additive quantity, therefore at a particular wavelength, the sum of all the absorbance should be equal to 80. The concentration of potassium permanganate and potassium dichromate can be determined simultaneously by the measurement of absorbance of a mixture solution at two wavelengths, at which the difference of molar absorptivities are large to get greatest activity. Now, the instrumentation. The instrument which we use here is the spectrophotometer. So, what is spectrophotometer? Spectrophotometers are the instrument which are working at a wavelength where the absorption is maximum. Such wavelength of the radiation whose absorbance is maximum is called lambda max. A spectrophotometer is employed to measure the amount of light that a substance absorbs. The instrument operates by passing a beam of light through a sample and measuring the intensity of light reaching a detector. The extent to which a sample absorbs light strongly depends upon the wavelength of light. The measurement of absorbance at a particular analyte is preferably made at a wavelength at which the absorbance of that analyte or species is maximum, known as wavelength of maximum absorption. For the determination of wavelength of maximum absorption measurements must be made at numerous wavelengths in order to obtain an absorption spectrum. An instrument of a single beam type uses one beam of radiation and passes it through a single cell. With the help of spectrophotometer, we can have qualitative as well as quantitative analysis of any two types of sample. It may be solid, liquid, or a gas. It may be colored or colorless. The spectrophotometers are of two types: single beam spectrophotometer, double beam spectrophotometer. The type of spectrophotometer which we use here in this experiment is a single beam spectrophotometer. An instrument of the single beam type uses one beam of radiation and passes it through a single cell. Single beam instruments are generally less expensive than double beam instrument. So following are the main components of a single beam spectrophotometer. The first one is the light source. First is the source of radiation. It may be UV light, visible light, or IR radiations. UV light can be obtained by heating the filament, which is filled with either hydrogen gas or deuterium. Visible radiations can be obtained by incandescent lamp with tungsten filament, and IR radiations can be obtained by heating Newton's glower at the temperature of 15 to 2000 degrees Celsius. The second comes the collimatic convex lens. Function of the collimatic convex lens is to collect all the rays coming from the source, and then there is a diaphragm. It is used to set 100% transmittance. Next comes the monochromator to obtain radiations of one wavelength. A monochromator is an optical device that transmits a mechanically selectable narrow band of wavelength of light or other radiations from a wide range of wavelengths available at the input. The main function of a monochromator is to separate the color components of a light. It can use either the optical dispersion phenomena in a prism or that in a diffraction grating. Thank you so much. Now my other group member Fatma Altaf will carry on this presentation.
Assalamu alaikum. My name is Fatma Altaf and I will continue the presentation from here. So now, moving on to the sample holder or cuvette, in which the sample will be placed. As you can see, there are three types of cuvette according to the light source. For UV light, it should be made of quartz. For visible light, it should be made of glass. And for IR light, it should be made of rock salt. And if you want to measure the intensity of incident light, you must remove the sample. After it, when all the light can pass through easily, so after some part, if you want to measure the intensity of incident light, you must remove the sample so all light can pass through easily. So after some parts of radiation absorb in cuvette and remaining is transmitted through detector. So a detector converts a light signal into an electrical signal. Spectrophotometer normally contains either a photomultiplier tube detector or photodiode detector. Moving on to the equipments. We have spectrophotometer, which measures absorbance. The second one is distilled water for making up the volume. Now, the third one is 25 ml volumetric flask. And the last is watch glass to weight potassium dichromate and potassium permanganate. Now, the procedure starts. We have to measure accurately 0.5 to 0.6 gram of potassium dichromate and potassium permanganate. And then prepare standard solution in two different volumetric flasks of 25 ml. Now the next point is transfer 5 ml of standard KMNO4 and potassium dichromate, which we have prepared just before this in 25 ml volumetric flask. Transfer 5 ml of it, and without making the volume, note its absorbance at lambda max of potassium permanganate and potassium dichromate respectively. After this, transfer 5 ml of potassium dichromate and potassium permanganate in another 25 ml volumetric flask and make up the volume now. And note its absorbance at lambda max of potassium permanganate and potassium dichromate respectively. Moving towards, now take 10 ml of sample solution in 25 ml volumetric flask and make up the volume up to the mark. This will be the last step probably. Now note its absorbance at lambda max of potassium permanganate and potassium dichromate respectively. Thank you so much. Now my last group member will continue from here.
Assalamu alaikum. I am Humaira Gabol. I will continue the rest of the part of this presentation. Now let's move on to observations. The observation for this experiment are: amount of potassium permanganate is equals to 0.5049 grams. Amount of potassium dichromate is equals to 0.5012 grams. Molar mass of potassium permanganate is equals to 158.034 gram per mole. Molar mass of potassium dichromate is equals to 294.185 gram per mole. The lambda max of manganese plus 2 is 545 nanometer. The lambda max of chromium is 440 nanometer. As you can see, the observation table drawn here, which shows the absorbance values recorded at both the wavelengths 440 nanometer and 545 nanometer of these solutions. Since we know that the absorbance is an additive quantity, which means the individual absorbances of the species is equal to the total absorbance. AT is equals to A1 plus A2 plus A3 and so on. Similarly, we have two absorbing species over here, potassium dichromate and potassium permanganate. By expanding the above equation, it becomes AT is equals to epsilon of potassium dichromate into B, path length of the cuvette, into concentration of potassium dichromate plus epsilon of potassium permanganate into B, into concentration of potassium permanganate. Now moving on to the calculations. For the calculation, in the first step, we have to determine the molarities of potassium permanganate and potassium dichromate with the help of the given formula. So for the molarity of potassium dichromate, molarity is equals to amount multiplied by 1000 divided by molar mass multiplied by volume. Here volume is the volume of the volumetric flask in which we prepare the standard solution of potassium dichromate. By putting the values and solving it, we got the molarity of potassium dichromate is equals to 0.0681 molarity. Similarly, with the above formula, we will now calculate the molarity of potassium permanganate. After putting the values and solving it, we got the molarity of potassium permanganate is equals to 0.1278 molar. Now in step number 2, we have to calculate the molar absorptivity values for potassium dichromate and potassium permanganate by using Beer-Lambert's law, which is A is equals to epsilon into B into C. Here A is absorbance, B is the path length of cuvette, and C is the concentration of individual absorbing species. At 440 nanometer, we have to calculate the epsilon values of potassium dichromate as well as potassium permanganate. For dichromate, by rearranging the formula and putting in the values of path length B and absorbance A, we got the epsilon value of chromium 14.42 molar inverse centimeter inverse at 440 nanometer. Similarly, for potassium permanganate, we got the epsilon value 0.1799 molar inverse centimeter inverse for manganese at 440 nanometer. Now at 545 nanometer, we did the same thing like we have done at 440 nanometer. At 545 nanometer, we calculate the epsilon values for potassium dichromate as well as potassium permanganate. The epsilon values for the epsilon value of chromium is 0.602 molar inverse centimeter inverse, and for manganese is 3.043 molar inverse centimeter inverse. Now in step number 3, we have to determine the concentrations of both the species by using formula of simultaneous determination. Mixture without dilution at 545 nanometer, the total absorbance is equal to the absorbance of manganese plus absorbance of chromium. AT is equals to absorbance of manganese plus absorbance of chromium. By expanding the absorbance formula and putting in the values of epsilon in the above equation, we have the equation 0.208 is equals to 3.043 concentration of manganese plus 0.602 concentration of chromium. Solving it for the concentration of manganese, it becomes equation number 1. Now at 440 nanometer, the total absorbance is equal to absorbance of manganese plus absorbance of chromium. AT is equals to absorbance of manganese plus absorbance of chromium. AT is equals to epsilon of manganese into B concentration of manganese plus epsilon of chromium into B concentration of chromium. Here by putting the epsilon values of manganese and chromium at 440 nanometer, we got 0.213 is equals to 0.1799 concentration of manganese plus 14.42 concentration of chromium. Putting the values from equation 1 into equation 2 and solving it for chromium, we got the concentration of chromium, which is 0.0426 molar. And by putting the value of chromium in equation 1, we will get the concentration of manganese, which is 0.0599 molar. Now, now for the mixture with dilution, here calculations are same as we have done in without dilution. At 545 nanometer, the equation 1 is concentration of manganese is equals to 0.042 minus 0.602 concentration of chromium divided by 3.043. This is equation number 1. At 440 nanometer, the equation 2 is 0.094 is equals to 0.1799 concentration of manganese plus 14.42 concentration of chromium. Now putting the values of equation 1 into equation 2, we will get the concentration of chromium, which is 0.0194 molar, and then putting this value into equation 1, we will get the concentration of manganese, which is 9.9901 exponent minus 3 molar. For sample, by using simultaneous determination formula, the equation 1 is the equation 1 over here is concentration of manganese is equals to 0.062 minus 0.602 concentration of chromium divided by 3.043 at 545 nanometer. At 440 nanometer, by rearranging the formula, we have equation number 2, 0.092 is equals to 0.1799 concentration of manganese plus 14.42 concentration of chromium. Now, by putting the values of equation 1 into equation 2, we will get the concentration of chromium, which is 0.0187 molar, and then putting this value in equation 1, we will have the concentration of manganese, which is 6.572 exponent minus 4 molar for the sample. Now, so in the results, we report the concentration values of sample over here. The concentration of manganese plus 2 by simultaneous determination is found to be 6.572 exponent minus 4 molar. The concentration of chromium plus 3 by simultaneous determination is found to be 0.0187 molar. So, the whole summary of this presentation is that we can determine the concentration of different species present in a mixture by using simultaneous determination method. So this is the end of our presentation. Thank you for watching us.